All right, let's dive in. Today, we're talking about a book that is, and I'm not exaggerating here, absolutely essential for any software engineer. Martin Kleppmann's Designing Data-Intensive Applications. Now, we're not just going to give you a book report. Nope. Our goal is to pull out the core ideas, the mental models that will fundamentally change how you look at building systems. Okay, so right out of the gate, Kleppmann lays it all out. This book isn't about finding some magical one-size-fits-all database. It's really about a whole philosophy. The core idea? Every single choice you make is a trade-off. There's no free lunch, and the only way to make good choices is to understand what's really happening under the hood.
So that's the big question, right? If there's no single best answer, how on earth do you even begin to choose the right tools? How do you make those trade-offs? Well, think of Kleppmann's book as our guide, and our journey is going to start in the simplest place possible.
All right, let's start small. Imagine just one computer, one application. Super simple, right? Well, not really. Even here in this tiny little world, you're immediately slammed with these huge decisions that can make or break your performance. And it all boils down to one very basic question.
I mean, really think about this for a second. You save some data, I don't know, a user's profile, into a database with millions, maybe billions of other records. And when you ask for it back, poof, it's there in milliseconds. How? That's not magic. It's all thanks to a really clever fundamental data structure.
And that structure is called an index. The best way to think about it, it's just like the index at the back of a textbook. You wouldn't read the whole book from start to finish just to find one term, would you? Of course not. You'd flip to the index, find the term, and it tells you exactly what page to go to. That's what an index does for a database. But, and there's always a but, even here we hit a critical trade-off. And this is our first big showdown. In one corner, you've got B trees. Think of these like a perfectly organized library card catalog. Everything is in its right place. Amazing for finding stuff fast. That's what we call read optimized. But in the other corner, you have LSM trees. These are more like a diary or a logbook. You just keep adding new entries at the very end. Super, super fast for writing. But, finding something specific later on means you have to do a bit more work. So what do you choose? It completely depends on your workload. Are you doing a ton of reads or a ton of writes?
Okay, but let's be real. A single machine isn't going to cut it for long. If you want a system that's reliable, that doesn't go down and can handle a lot of users, you have to use multiple machines. But the second you do that, you unleash the biggest source of chaos and pain in system design, the network.
So the most common way to deal with this is something called leader-based replication. And it sounds pretty simple, right? It's a logical flow. All the writes, all the new data go to one main machine. We call it the leader. The leader then turns around and broadcasts that change to all the other follower machines. This way, everybody has a copy. If one machine dies, no big deal, the others are ready to step in. Seems totally straightforward, doesn't it? Yeah, well, here's the catch. The network is not instant. There's always a tiny delay between the leader getting an update and the followers hearing about it. We call this replication lag. And this creates a super frustrating problem for your users. Imagine this. You post a brilliant comment on a website. You immediately hit refresh to admire your work, and it's gone. What happened? Well, your refresh request probably went to a follower machine that hadn't gotten the update yet. As far as that machine knows, your comment doesn't exist. To you, it just looks like the website ate your data.
So this whole lag thing, it's really just the tip of the iceberg. It points to a much deeper, way more complicated problem. How in the world do you get a whole bunch of independent computers to agree on what the actual truth is, especially when the network connecting them is totally unreliable? This is the grand quest for consensus in distributed systems. And let me tell you, it is a hard quest. Why? Because you're dealing with all these ghosts in the machine. Data packets can just vanish or show up late or even arrive in the wrong order. And get this, every computer has its own clock and they're all slightly off. So you can't even trust timestamps to figure out what happened first. And maybe the weirdest one, a machine can just pause for like a few seconds to do some internal cleanup. It's not crashed, it's just AFK for a moment. All this uncertainty makes getting everyone to agree on a single truth incredibly, incredibly difficult.
So, what's the ultimate prize in this quest? It's a property called linearizability. This is the absolute gold standard, the strongest guarantee you can possibly have. What it means is that even though you have this messy, complex system spread across tons of machines, you can make it act like there's just one single copy of the data. When an operation is done, it's done. It's instantly visible to everyone, everywhere at the exact same time. It's about making the complicated feel simple.
Now, this is a point where a lot of people get tripped up, so let's use this table to make it super clear. You'll hear about serializability and linearizability. They sound similar, but they're different. Serializability is about groups of operations, or transactions. Think of it like a bunch of librarians shelving books at the same time. As long as the library ends up in a correct state, we don't really care about the exact order they did their work in. It just has to look like they did it one after another. Linearizability, on the other hand, is much stricter, and it's about a single thing, like one specific book. It guarantees that at any given moment, everyone agrees, is that book on the shelf or is it checked out? There is no in-between, no ambiguity. It's one or the other. Okay, deep breaths. So, we've wrestled with reliability and consistency. We figured out how to store our data safely across a whole fleet of machines. Awesome. But, so what? Data sitting in a database isn't very useful. The next big step is putting that data to work. How do we actually use it to create value, to find insights, and to power our applications? And right away, we hit another fundamental fork in the road. On one side, you have batch processing. This is for when you have a huge but finished set of data. Think all of yesterday's sales data. You run a big job on it, it might take a few hours, but it chews through the entire thing. On the other side is stream processing. This is like trying to drink from a fire hose. It deals with a never-ending, unbounded river of events as they happen, right now. The goal here is super low latency, like milliseconds. So are you generating a monthly report? That's batch. Are you trying to detect credit card fraud the instant it happens? That's got to be streaming. Two totally different worlds. Okay, so let's pull back for a second. We've gone from indexing on a single, tiny machine all the way to processing massive data streams across a global cluster. And through it all, there's been one theme that just keeps popping up over and over again. And this, right here, is the core philosophy of this entire book. So if you're going to remember anything, remember this. First, everything. And I mean everything is a trade-off. You want perfect consistency? You're probably giving up some availability. You have to choose. Second, distributed systems are hard because networks are unreliable. They will fail. Don't hope they won't. Design your system assuming they will. Third, don't treat your tools like black boxes. You have to understand what's going on under the hood to really use them well. And finally, words matter. Be precise. Terms like consistency aren't just fuzzy feelings. They are hard, specific, provable guarantees. And all of that brings us to this final, really powerful question that Kleppmann leaves us with. After we've mastered all the technical details, all the trade-offs, he asks us to look up and think bigger. As engineers, we're the ones building the systems that store, process, and control the world's information. So what is our responsibility to make sure those systems are not just fast, not just scalable, but that they're also correct, that they're fair, that they're built with a deep sense of ethical duty? That's the ultimate trade-off, and honestly, it's the one that matters most.